Now having done the common emitter amplifier to some detail, let us have a quick comparison between common emitter amplifier and common base as well as common collector. Now we will not have time to look into the detailed analysis of both common base and common collector. What I have shown here is a typical circuit which you would use for a discrete common base amplifier. So what we have here is you have, again you can see a potential divider here, and you are given a biasing very similar, and you have a resistance Re here, and you have a resistance Rc and Rl. Now there are two major differences here compared to what we saw in a common emitter. We see here the signal is now applied to the emitter. We said that in a common base amplifier, we said that the signal is applied between the emitter and ground. Now since we are using a voltage divider network to bias, get a certain value of VBE, we need to ensure that the base is at AC ground potential. This is done by connecting a capacitor from base to ground, a fairly large value capacitor. Now in this case we will not analyze it, but just by looking at the circuit we can see that the output side is very exactly, almost exactly same as what we saw for the common emitter amplifier. Therefore the output resistance is high. In a common emitter amplifier the output resistance was typically Rc, and that is generally Rc would be a few kilo ohms. So the output resistance was quite high. Now we know that the output resistance of a voltage amplifier should be ideally 0, but that is not satisfied by a common emitter amplifier. The same problem is here in a common base amplifier also. The output resistance is quite high. Now here, since you are applying the input signal to the emitter here, if you look at the equivalent circuit, you would see that the input side would have capital Re coming in parallel with small re, and we know that small re is a very small resistance. Therefore the input resistance will be small re, which is an extremely small value. So this is one of the major difference between a common emitter amplifier and a common base amplifier. In a common base amplifier the input resistance is very low. Now coming to the voltage gain, we see that in fact you get the same expression for the voltage gain here, except that the sign, there won't be a negative sign. In a common base amplifier the expression for the voltage gain would be positive, would have a positive sign. Now this is because of the reason that if you look at the model, you will see that the way the signal is applied. In the previous case the signal was applied to the base, therefore any increase in value of the base voltage resulted in an increase in collector current, which decreased the VCE. In this case it is the other way, and that is why we see that there is no the voltage gain would be, there is no negative sign. Now what is the application of a common base amplifier? Now common emitter amplifier, we said that even though its input resistance is not very high, output resistance is not low, still for simple modest application you could use a common emitter amplifier. Now common base amplifier, the input resistance being very low, can be used as a current amplifier. If you remember in our towards the beginning of today's lecture, I said that a current amplifier should have low input resistance. So common base amplifier you could think of as a current amplifier. And another interesting application of a common base amplifier is its high frequency response. It has a very good high frequency response. We would see some of this later in another lecture. So now let us look at the common collector amplifier. This also has another name which is called the emitter follower. Now again looking at the circuit, what we have is you have the input connected through a capacitor, the circuit here, and we see here that we are not using the standard potential divider here. That is there for a very important reason. we will see that in a minute. And so we would choose RB, a fairly high value of RB would choose, and the output is taken from the emitter, and you would have a coupling capacitor there, and you would have the load RL here. Occasionally you might use the RE, which is used for biasing itself, as the load resistance. Now in this case, this you would see that is very similar to what we did for the common emitter amplifier with no emitter bypass capacitor. So you would see the input side is very similar to that, and there we saw the input impedance or input resistance we saw was RB parallel beta plus 1 times small re plus capital Re. Now here also, if you consider this a short circuit, instead of Re you will have Re parallel RL, but you would see that the input resistance would be now quite high. So here is a situation where your input resistance is very high. Now the output resistance is quite low. This is because of the reason that you are taking the output from the emitter. Please recollect that both for the common emitter and the common base, the output was taken from the collector, and the collector terminal was a current source. We had a controlled current source there, and because of that you had a high resistance there. Whereas here you are taking the output from the emitter, and we know that the emitter terminal and the impedance looking into the emitter is quite small. So in this case you would see that the resistance you have, the output resistance is quite small. Now here the voltage gain is approximately unity. So here is an amplifier where your gain is unity, but this circuit has very high input resistance, very low output resistance. Therefore this is a very useful circuit. This is used as a buffer, and you can think of this similar to the voltage follower using an op amp, and that is why the name emitter follower is given here. The main difference being, in a voltage follower the impedance you get is almost infinite, because in a voltage follower, since you have output directly connected to the negative terminal of the negative input of the op amp, you have an extremely high value. The input resistance, open loop input resistance, gets multiplied by an extremely large value, which is almost infinite, but here the value is not that high. Again later we would see in another lecture how we could increase the value of the input resistance. So we see that in comparison, the common emitter, the common base, and the common collector. So we see that from the impedance point of view, we see that the common base is extremely low input impedance, whereas common emitter has higher, whereas common collector has the highest. So from the input impedance point of view, common collector is the best. Now from the gain, voltage gain point of view, we saw that both common base and common emitter gives you same gain, but common base cannot be, amplifier cannot be used directly as a voltage amplifier, since the input impedance is quite low. So that is why most of the time we would find that a common emitter amplifier is the most preferred choice. Now we can have a quick look at the high frequency hybrid pi model. In the model which we used so far, we had only R pi, R naught, and GMV pi. Now in the high frequency model, what we have here, we have two more capacitors here. There is a capacitor here called C pi, and you have a capacitor between the collector and this B dash terminal. Now the output base, the base terminal is the B here, and the B dash terminal is the inside terminal, and you can think of this R this resistance R here, the RB here as the what is called the base spreading resistance, which is important in the when you analyze the circuit for high frequencies. Now in this particular model we have the device capacitors here. Now the we can have some insight into the performance of a common emitter amplifier without going into detailed analysis. We can have a quick look at the model and try to have an idea about the high frequency response of the common emitter amplifier. Now in a common emitter amplifier, so if we replace what we did earlier with this particular model, so if we replace the midband hybrid pi model with the high frequency hybrid pi model, what we would see is that we would find this C pi, which is the capacitance between the base and the emitter, and the C mu, which is a depletion capacitor. Now here we would see that when we do the analysis, we know that the collector terminal, we did earlier also from an analysis we saw that in a common emitter amplifier the output terminal is minus Gm times Rc parallel RL, and the times the input voltage, say in this case V pi. So think of a scenario where one side of the capacitor you have V pi and the other side of the capacitor you have minus of Gm V pi Rc parallel RL. Now what you would see that equivalently this is equivalent to multiplication of this capacitor C mu by the gain. So effectively when you analyze this particular circuit, we can represent this C mu as coming in parallel with this C pi multiplied by the approximately the gain of the common emitter amplifier. Now the typical voltage gain of a common emitter amplifier, let us say, would be about 100 or so. Now the value of C mu is typically about a picofarad or so, and the value of C pi would be about approximately 10 pf, 10 to 12 pf. So we would see that because of this negative voltage gain in a common emitter amplifier, the capacitor C mu gets multiplied by the voltage gain, and effectively you would have a huge capacitance sitting across the input side, which reduces the high frequency response. So coming to the frequency response, we earlier talked about the low frequency side. We said the low frequency response, we said, is primarily due to the coupling capacitors, and the high frequency response is due to these two capacitors which we found here. When if you do the analysis here, we would find that this high frequency response is like a low pass response, and typically the kind of high frequency cutoff frequency you get for a common emitter amplifier would be the order of, would be definitely less than megahertz. Now for a general purpose transistor, if you use a general purpose transistor like BC147 or 547, you would see that for a gain of, let us say, 100 or so, you would see that the high frequency cutoff frequency, the cutoff does not exceed about 200 or 300 kilohertz. So this is one of the major disadvantage of another disadvantage of a common emitter amplifier. The high frequency response is not good. Now here when we talked about common base amplifier, we said that the common base has very low input resistance. Another advantage of common base resistance is that the problem which we talked about here, now the multiplication of this capacitor C mu by the gain, which is called the Miller effect, is not there in a common base amplifier. This is because of the fact that we said in a common base amplifier we apply the input between emitter and base. So you would see that this capacitor, we know C mu is appearing between collector and base, and therefore this C mu now would be appearing parallel, and we know that value of C mu is quite small. So therefore, in the case of a common base amplifier, intuitively we can see that the high frequency response is quite high. So in a later lecture, we will talk about how we can combine the common emitter and common base and get a very high frequency response, also a very high gain, voltage gain. So we have come almost to the end of the lecture. Let us have a quick recap of all that we did today. Now we talked about different types of amplifiers. We talked about amplifier being a controlled source, and we also said that very often when we talk about amplifier, what we have in mind is a voltage amplifier. Therefore, we say that the input resistance should be very high, output resistance should be very low. And we said actually there are 4 types of amplifiers, but the most commonly used amplifier is the voltage amplifier. Again, coming back to the voltage amplifier, which is the most commonly used one, we said because we want to develop the entire signal voltage across the input resistance of the amplifier, we would like to have very high input resistance. So ideally, if we can keep Ri infinite, then the entire signal voltage would appear across the input resistance. And the output resistance, this being a voltage amplifier, we have a Thevenin representation here, and if you want to ensure that the entire voltage, that is A Vo times Vi, appears across V out or V naught across the RL here, then we need to have R naught very small or ideally 0. And this is why we always say, generally we say that the output resistance of a voltage amplifier should be low. But we must keep it in mind that we should apply this only for a voltage amplifier. We also talked about current amplifier, and we said when you talk about a current amplifier, the scenario is very different. In a current amplifier, the input resistance should be as low as possible, ideally 0. If it is a short circuit here, then the input signal is a current signal, and if your input is a short circuit, then the entire current would flow through the input of the amplifier, and the output, you have a Norton equivalent there. Therefore, in an ideal case, in a current amplifier, we should have high output resistance, so that the entire current I naught flows through the load. Then we talked about a public address system. We said a typical application, we can keep it in mind, and we said in a typical application like a public address system, you have a sensor, which is a microphone, which gives you some output which needs to be amplified, and an amplifier generally in a public address system, you need a pre-amplifier. This is because of the reason that the microphone output is very small, and the impedance of if you consider it as a voltage source, the impedance is very high. So the pre-amplifier in a public address system ensures that you have a very high input resistance and also an extremely low noise pre-amplifier. So in a public address system, you would have a pre-amplifier, which is a low noise amplifier, followed by a post amplifier. Now if you have a discrete amplifier, that is where you can think of maybe using a common emitter amplifier. So we see that common emitter amplifier, because of its low input resistance, cannot be directly used along with a sensor, especially with a microphone or so. You could use it in between stages. And finally, in a public address system, you need to develop the signal across a loudspeaker, which is extremely low impedance, 8 ohms, 16 ohms or so, and that is where we use a power amplifier. This is one of our lectures later on. Now then we talked about op-amp being an ideal voltage amplifier. Interestingly, in an op-amp also, how did an op-amp achieve such an ideal, how did it become an ideal voltage amplifier? One thing we said is because of the negative feedback. Now another thing to keep in mind in an op-amp is, if you look at the inside of an op-amp, essentially you have 3 blocks inside an op amp. The first block is a differential stage when you talk about a 741, and that stage takes care of the common mode rejection ratio, and also has a gain of typically 741, typically a gain of 10 power 3, followed by a post amplifier where another gain of 10 power 3. So altogether approximately 10 power 6 gain is picked up, and in a 741 you have a final stage which is an output stage. So you would see in most of the applications you would find, say, these 3 blocks, a first block, let us say, like a preamplifier, a middle block like a post amplifier, and a final block like an output stage. Now there were a lot of questions on biasing and so on, and we said discrete amplifiers, even though they are not ideal, they have their place because you can build them, but the major minus point of the discrete amplifier is that because there are too many components, the reliability is low, and also you need to design it very carefully, and the gain and the other parameters can vary with time and also with different devices. Now there were a lot of questions on biasing. Now what is the need for biasing? I hope it is clear. After today's lecture things are very clear. Now the purpose of biasing is to choose an appropriate point on the IC/VC characteristics, and you need to choose this point such a way that you are far away from saturation as well as cutoff. So you would choose a point somewhere in the middle depending on the value of IC you want, and you would choose, for example, in the design example given to you, you are given a VCC value of 10 volts. So you would choose a VCE value and IC value depending on the constraints given. So biasing essentially is an exercise to choose a point, an appropriate operating point, so that you can get the desired gain and so on. Now we also talked about good biasing circuits and bad biasing circuits, and we said that these 2 circuits which is said are bad because they cannot keep them from thermal runaway, any temperature variations, and the op amp, the BJT being having a negative temperature coefficient for its VB, we said it will cause thermal runaway, and we said that this circuit is bad because this cannot prevent it, and we talked about the second circuit being bad, saying that this particular circuit is designed for a particular value of IB, and that cannot be, if there is a variation in IB from one device to another device, then this circuit fails. And we said that the most commonly used circuit is the one with 2 resistors at the base and a resistor at the emitter, and this is a circuit which we are going to use tomorrow. And what we did is, we said the kind of thumb rules are you would choose a VBB value for the base value, and the VC and the IC RC to be roughly 1/3 VCC. So in your design example you could take care of this, and we also said that to take care of the beta variations, you would make sure that the current flowing through R1 and R2 is much higher than the base current. So you ensure that by making sure the current through R1 plus R2 is approximately 10% of the emitter current. Then we talked about small signal approximation, which is very, very important. So therefore we said that in a common emitter amplifier, we assume that the input signal which you superimpose on the DC is much smaller than Vt. So typically we said the value we are talking about is about 10 millivolt or so, and if it is not, you would have a lot of distortion. Very often, we also said very often you do not see this on an oscilloscope, but actually if you see it on a signal analyzer, you would see distortion. And so depending on the application, you need to take this in mind. Then we talked about hybrid pi model. We said this is an extremely good model, and where we have 2 small signal parameters, GM and R pi, and if you take the early effect also into consideration, we have small R naught, and with this we said a common emitter amplifier can be analyzed easily, and we got the parameters of the common emitter amplifiers, and what we found that was the input resistance was quite small, R pi, which is about a few kilo ohms, and whereas we found that the gain was quite high, maybe about 100 or so, but the output resistance again was quite high. So we said that common emitter amplifier is not a good candidate as a voltage amplifier. It's ideally suited as a kind of a post amplifier, and we also said we need to keep it in mind the overall voltage gain in an application where the resistance, the signal source resistance need to be much smaller than the input resistance. Now later we talked about T model. We said that's a very useful model when we talk about whenever we have a resistance in the emitter. We find that T model gives you much an easier way to analyze the circuit, and we saw a common emitter amplifier with a series emitter resistance, and we found that in this case compared to the previous common emitter amplifier with a capacitor, the emitter, the input resistance here was much higher, but the voltage gain was very low, and we said the output resistance was the same, and we said both the amplifiers, common emitter amplifiers, were unilateral amplifiers, where meaning the whatever you do at the input is not affected at the output. So any variation in the load resistance does not change the input resistance, or any variation in the signal source resistance does not change the output resistance. Then we compared the common emitter amplifiers with the common base and common collector, and we said common base is a good candidate, we said, as a current amplifier, and it has also very good high frequency response. It has a very low input resistance, therefore it cannot be used as a voltage amplifier. We talked about common collector amplifier being as a very good choice as a buffer, and finally we talked about the high frequency model, and we said that common emitter amplifier again has low high frequency response because of the Miller effect. So this brings us to the close of this lecture here. Thank you.